Okay, so good morning, everyone. Today we will cover two topics. The first one is the task of separation and classification. And we will see how to formulate these problems as convex optimization problems, meaning problems which are relatively easy to solve using those methods which we have already covered, which means either by linear programming or quadratic programming. So the task that we are looking at in these separation and classification tasks usually is that we have two sets of points which have certain properties. So the color and the shape of the points here defines the property of individual points, which means that we have a bunch of blue points which share the same property and a bunch of red points which again have some different property. And we would like to find some kind of dividing line between these two sets of points, meaning we would like to find what makes some point a blue point and what makes some other data point a red point. And these kind of problems, they can occur in practice, imagine that we have two types of production units which have to be separated by a wall. So essentially the task of separation here is to find the properties of a straight line which represents the wall here, which strictly separates the blue points from the red points here. So that would be kind of the physical interpretation of this problem. But this problem occurs very frequently, especially in data analysis, when we want to kind of assess whether some new measurements belongs to one set of points or to the other set of points. Like imagine that these are the points which represent some quality criteria of the products which our company produces. Then the blue points here are the good points and the red points are those products which have failed some quality check. And these kind of properties, they can be assessed by taking measurements, going to the laboratory and doing some kind of analysis of the samples. But what we would like to do is to avoid that lengthy and probably cost-consuming analysis. Instead, we would like to devise a separation function which will then tell us that if we would get a new point as the measurement, then we can immediately assess whether the point belongs to the good set or to the bad set just by checking whether the point lies to the left or to the right of this separation line. So this is essentially what separation and classification is about. These two problems, they are tightly related. Separation deals just with two sets of points. In classification, we can have multiple sets of points, like very good product, middle quality, and poor quality. But the idea is the same, to devise a function which separates these sets of points. And sometimes this problem is easy, like in here, because we see that we have actually many options how to devise this separation function. However, the points can also be like this. Okay, so here we also have strict separation, but for whatever reason, this kind of separator might not be preferred, because we see that it is really close to individual data points, while we see that if we would devise some other function, for instance a straight function, then it would have much larger margin between the separation line and the individual points. So from practical purposes, this separator, even though it is the so-called strict separator, might not be preferred. And even worse, what can happen in practice is that there might be data points which cannot be separated by a straight line in a strict manner, because whichever line we choose, we will always have some points which lie on the wrong side of the separation function. So for instance, we would like all the empty circles to be to the right of this separator, but we have this point here which is to the left. Okay? So then if we still insist on having a straight separator, meaning a linear function which separates these two sets of points, we have to make some compromise, like Okay, so we see that we cannot strictly separate these two sets of points, but at least we might find a function which minimizes the number of wrongly classified points. So here it is actually one point which is wrongly classified. This one, well, probably it is straight on the line, and there are no black points which are separated in a wrong way. So here we have found a separator which at least minimizes the number of wrongly classified points. And the final example might be that if we relax that requirement of having a linear separation function, then we might look for some kind of non-linear separator, because that gives us larger freedom, and we might obtain strict separation even in this case. And here we see that there would be no linear separator between these two sets of points. So this is essentially the problems that we are going to look at. And depending on what type of the separation function we choose, we might aim either for pure linear separation. I should add, this is the linear strict separation, meaning we would like to find the dividing wall such that one set of points is strictly on one side, the other one is strictly on the other side. Then we still might have kind of multiple options how to devise this linear separation function. So then among all those options, we might look for the most robust separator, meaning the one which has the largest separation gap between the function and individual point. Then, if it is not possible to divide two sets of points by a linear function in a strict manner, we will aim at least minimizing the number of misclassified points, and these kind of separation problems are called approximate separation. And then we will kind of combine the robust separation with the approximate approach, and we will cover something which is called support vector machine. And this is actually a very well-known technology that is often used in practice, for instance, when recognizing people from images taken by a camera. And we will cover certain of those applications in this lecture. And then finally, we will also touch on nonlinear separation, where we would like to find some nonlinear function which strictly separates two sets of points. So this is essentially our outline for the first part of the lecture. So let us first take a look at the linear separation scheme. So yet again, we are given two sets of points, and our objective is to find a linear function such that all black points are to the left of the function and all white points are to the right. Okay? So mathematically, the problem that we are going to look at is that we have two sets of points. So notice that we have this curly bracket. A curly bracket always means it is a set. Each of these x's here, that's the position of individual black circles here. So each of these is a vector, because we are assuming here a two-dimensional case, but we can do these separation problems in arbitrary dimensions. So we have one set of points, and then we have y's that would be for the empty circles. And technically what we are looking for are parameters a and b of this linear function here. So a transpose times x plus b, that's clearly just a linear function in a two-dimensional space. Usually we would write a linear function in 2D space by y is equal to ax plus b. Okay, but we are treating both y and x as the coordinates of individual points. So we are just aggregating the tangent of the linear function, meaning the slope of the function, into this vector a, and then this scalar b is just shifting the linear function with respect to 0. Okay? So we have a linear function a transpose x plus b. And for strict separation, what we require is that the full points, meaning the x's here, are on one side, and the y's, meaning the empty circles, are on the other side of this linear function. And we can do that by saying that one side means that the function evaluated at those data points, which represent the black circles here, that this function is positive for all black circles, and for all white points, the function must be negative. Actually, here we can use arbitrary relations. So we can even assume that for x points we have less than 0, and for y points we have larger than 0. It doesn't change anything. Okay, so you can choose whichever relation you want. Okay, so that's what we are looking for. We would like to find the parameters a, which is an n-dimensional vector. So each of these data points is also an n-dimensional vector. So a is represents the tangent of the linear function, and b is the constant offset, and these are the optimization variables. And we would like to find these two variables, which are our optimization variables, such that these constraints hold. Now, can somebody tell me what kind of an optimization problem is this? It is an optimization problem, even though it is not written in the standard form that we have usually assumed. So usually we assume that an optimization problem is that we are minimizing some objective function, which is the function of the optimization variables, and we have some constraints. And we might have inequality constraints, and we might have equality constraints. This is the most general description of an optimization problem. Now the question is, the problem as stated on this slide, is it an optimization problem? What are the optimization variables? Okay, so our vector of optimization variables, this z, would be a and b. Okay? Now the question is, what is the cost function? What are we trying to optimize? Why? One option is to minimize sum of squares of what?
Of the distance of the point from the line.
Why? Why would we need to do that? We will do something like that later on. But the point is, this is the simplest possible interpretation of a separation. So here we do not require that we care about the distance of the line from the points. We don't care.
So just the points are above or below the line.
Yeah, and that is exactly what our constraints are. Okay, so here in these constraints we have A transpose xi plus b must be larger than 0. Of course, we have to repeat this for every data point in the X set. Let's call that capital N. And we have the other constraints for the other data set. So here we have M points, capital M. So we might even have a different number of points. Okay, so these are the constraints. We see that they are kind of related to those inequalities. As stated, we have no equality constraints. But the question is, what about the cost function? What are we trying to optimize? How is the problem really stated? What do we want to achieve? Also in
one set of points should be all above.
Sure. Yeah, that's what's said by these constraints. So what the objective function says, if there are multiple options, let's pick the one which minimizes the cost function. Now the point is that on the slide we don't say what should happen if we have multiple options. And we clearly do have multiple options because we can rotate this line slightly and still obtain a strict separation. So the cost function would then say, if there are multiple options to achieve strict separation, pick the one which has the lowest value of the cost function. Essentially here we are saying, we don't care what is the function as long as it satisfies these constraints. So essentially what we are saying is we don't care about the cost function. And problems of that form is, and they are absolutely valid, if you want to say we don't care, then we just remove the cost function, but we still need to minimize something. So we just minimize a constant. Essentially it can be an arbitrary constant. And since it can be arbitrary, the convention is that we minimize 0. Essentially what we are saying, all choices of A and B which satisfy these constraints are equally good. So the optimization is actually free to pick any value. This is the so-called feasibility problem, and we have seen it previously. And we have also said that usually finding a feasible solution is somehow easier than finding the optimal solution. Okay? So we are actually preferring to solve feasibility problems because they are typically faster to solve. Okay? So the problem that we are going to solve is the minimize zero. Once you see this, you notice that it is just a feasibility problem. And we have just inequality constraints, and we might even convert them into this standard form. Okay, so we have to negate this term, so multiply it by -1, and we have these constraints. Okay. Now the only trouble here is that we are using strict inequalities. And now this is what makes a difference between theoretical mathematics and practice. Okay? Because we are going to solve these problems numerically using some software. Now, on a computer, which number is strictly greater than 0? Okay? I mean, it can be like number like 1 to -16, which is like the typical lowest precision if we take, for instance, MATLAB. I mean, is this a positive number? Well, strictly speaking, it is. But what would that mean for these points is that that line will be really close to one of those points. And it might even be a numerical problem. And in fact, the inequality would be like this. Now, if this left-hand side is -1 to the power of -16, I mean, is the constraint satisfied or not? I mean, we have a problem with precision in the computation. To keep the long story short, in optimization, if you want to solve it numerically, we always do require non-strict inequalities. So we cannot really solve numerically in a reliable fashion problems which have strict inequalities. So that's why all the software that we use to solve these kind of optimization problems does not accept strict inequalities. If there is a software which claims it can solve optimization problems with strict inequalities, either it is a mistake in the documentation and they really meant non-strict inequalities, or, although it is a bold statement, they are lying. Okay? There are some special procedures which can deal with strict inequalities, but you should not trust them very much. So basically, in practice, all software works with non-strict inequalities. So now the question is, if we want to solve this problem using a software which only accepts non-strict inequalities, how can we convert this problem into a non-strict form? Okay, so if we have g of z, which is strictly smaller than 0, we can convert it to a non-strict inequality how? Which tolerance? Like epsilon would be the tolerance, and what now? So is this the same thing?
Minus.
Well, depends on what the tolerance is. Okay? But usually tolerances are positive. Okay? So if the tolerance is positive, what do we need to do more here? We have to put a minus here. Okay? So this is basically what, even if a software takes strict inequalities, inside what it does, it converts them into non-strict inequalities by using some kind of tolerance. And if it does it automatically, it's better to do it manually, because then we have bigger kind of control over what the tolerance really is. Okay? And the typical tolerances which are used for numerical procedures to convert strict inequalities into non-strict inequalities are usually something like 10 to the power of minus 6. Okay? Not 16, but to the power of minus 6. Okay? So that's the typical tolerance that we use. So that's precisely what we do here. So we convert this problem into does not care about what the cost is, subject to minus A transpose xi minus b less than minus epsilon. And here we would have A transpose yi plus b smaller than minus epsilon. Okay? And now there is a final thing here. We might solve this problem immediately if we want, but the point here is that A and B are both optimization variables. This epsilon here, that's just a constant. We usually don't optimize it, but we just fix its value. Since it is constant, what we can do is we can divide both sides of the inequality by this epsilon here. What we would obtain then is we would minimize 0 subject to, and here we would have something like minus A transpose divided by epsilon. I mean, we can divide by epsilon because we assume that the tolerance is strictly positive, times xi minus b over epsilons less than minus 1. And here it's A transpose yi plus b over epsilon less than minus 1. Okay? And here the point is that we will denote this as the new optimization variable. We will call it A tilde. And this would be the new b that we will be optimizing. So this would be b tilde. And the point here is that this version of the problem, so the final version that we are going to solve is minimize 0 subject to minus A tilde transposed xi minus b tilde less than minus 1, and here A tilde transposed yi plus b tilde less than minus 1. The difference between these two problems is that this one has much better numerics than this one, because we are using nice numbers on the right-hand sides of the constraint.
It has to be A tilde transpose.
Yeah, it has to be A tilde transpose.
In this problem where we substitute A transpose, being that epsilon.
Oh, you mean that here, that
Yes.
this term here is A tilde transpose? Yes, thank you. Yeah. So the different, I mean, these two problems are absolutely the same, because we just divide it by a positive constant, and that doesn't change anything in the problem. It doesn't change the sign of the inequality. However, this problem from a numerical point of view is much more preferred because we have nice numbers as constants. And it's always better for the optimization to have nice numbers as constants rather than to have some large discrepancy. Notice that the the multiplier here is 1, right? The multiplier here is 1 to the power of minus 6. Okay, so we have 6 orders of magnitude difference between the constants in our problem. And this is what we mean when we say that the problem is well scaled. So this problem is well scaled because all constants by which we are multiplying have the same magnitude, or at least magnitude which is comparable. However, here we have magnitude which is significantly different. And solving this problem then might create problems in the software. Doesn't have to, but might. So essentially what we have done is that we have realized that Dividing by epsilon doesn't change anything, and then we can just optimize some new quantity. So we have essentially helped the solver to find the solution in a much more reliable way. So this is then the problem that we are going to solve at the end of the day. Okay? Now the question is, what kind of a problem is this? Which solver do we pick if we want to solve this problem? And so far we have covered unconstrained optimization, and we have seen various methods for that, gradient-based, random-based, and so on. We have covered like the Newton method, for instance. We have covered linear programming, quadratic programming. So which kind of algorithm can we pick to solve this problem? Well, we have to classify the problem. Okay? So what is the type of the objective function? What kind of a function is that? It's a constant. A constant function is a linear function. Okay, so we have a linear function. What about the constraints? We have to look at what the optimization variables are, and that's A tilde and B, and we have to look at whether they enter the constraints in a linear fashion. So is there any multiplication between the optimization variables? No. Those x's here, they are just constants. I mean, they are the locations of the data points. So all constraints are also linear in the optimization variables. So what is this problem? How do we call a problem which has linear cost function and linear constraints? That's linear programming. Okay? And it's always important to pick the correct algorithm, because clearly we can solve linear programming also by quadratic programming software, right? But we always have to find the most simple algorithm to solve a particular type of problems, because the simpler the algorithm, the faster we can expect to obtain the answer. Okay, so it's important not to overkill that, not to use too complex algorithm to solve a simple problem. Okay? So now we know that we are going to solve this problem as a linear program. Now, before we do that, we have to write it in the form of linear programming. And we know how linear programming looks like. Again, in the general case, it's minimization of a linear cost function. Again, z are the optimization variables, subject to equality and inequality constraints. Here we only have inequality constraints. So now the question is, if we know that we can use, for instance, LINPROG, and LINPROG requires us to provide the vector C, matrix A, and vector B, what would they be for this separation problem? So we can start by, well, we know what Z is. That's just A and B. So we essentially are comparing these two problems. So C transpose times Z must be equal to 0. Okay, so what is C? C is 0, 0, up to 0. Okay? Because then C transpose Z would be 0. What about the constraints? We have to write them into the, it should be Z here. By what should we multiply the vector Z, which is composed of A and B, such that we recover these constraints? So here we have minus, okay, we have to be careful, okay? Because we are multiplying by the vector Z from the right-hand side. So essentially what we can do is we can transpose each of these constraints. So what we can do is we can write it as minimize 0. There we don't do anything. Each of these guys here is just a scalar, because these are row vector and these are column vector, and the product of these two is a scalar, and B is clearly also a scalar. So we don't do anything wrong if we transpose everything. So if we transpose the first constraint, that's xi transpose times A. I will drop the tilde because it doesn't matter here. Minus B, smaller than minus 1, and here it's yi transpose times A plus B less than minus 1. Okay, now it's finally in the form from which we can deduce what the matrix A and the vector B is. Okay. So what is the multiplier of optimization variable A in the first constraint? That's minus xi transposed. What is the multiplier of B in the first constraint? Minus 1. and the right-hand side is -1. And we already have it converted into the standard form of less than or equal to. Okay? And then we do the same for the second one. Actually, here we can immediately expand because we know that we have to repeat these constraints for each point that we want to separate. So essentially, we are repeating these lines for all the points in the X set. And now comes the Y set. So again, the multiplier here is, well, for the first point, it would be Y1 transposed, and in B, we have just 1 as the multiplier. On the right-hand side, we have -1. And we are repeating this up to Ym transposed 1. And here we have actually -1. Okay? So then this is matrix B, and this is vector A. And now, finally, we will just call the solver. We will provide it with the cost function with the definition of the inequality constraint. And what the function returns is the optimal choice of A and optimal choice of B. And you will practice this in the exercises. Okay? So that's essentially what we have explained. Okay. So this is the pure linear separation. All we care about are these constraints, which we first convert into non-strict inequalities, and then we normalize these inequalities to get good numerics. So that's the final problem that we are solving. Since we don't care about the choice of A and B as long as it satisfies strict separation, that's why we have no objective function, in which case, by convention, we just minimize 0 here. So this is a linear program. Now we come to robust separation. Well, first of all, this is no separation at all, clearly, right? But these two are already separation functions. And they are strict separators because we see that both points lie on the respective sides of this separation function. So we see that we have at least two options how to choose that separator. And if we have multiple choices, why not to look for the choice which maximizes the so-called separation gap. So that's the gap between the function and the closest point to the function. Okay? And clearly we would like to find the compromise, meaning to situate the line such that it is basically in the middle between these 2 points. Okay? So the problem will be very similar to what we have looked at so far. So yet again, we have 2 sets of points. We would like the separator to be strict, but we would like to maximize the distance between these 2 points. By the way, let me say that it might be possible that not only this problem, but also the problem of pure linear separation does not even have any solution, like those points which cannot be linearly separated. Okay? Then the solver would just say the problem is infeasible, and it might still return some answer, some choice of A and B. But that's why you should always check the flag, the return flag of the solver, because if it says infeasible, you must not trust the numerical result which it gave you. It might look reasonable. I mean, those numbers might look interesting, but you cannot use them because it's just garbage which the solver has returned. So that's just as a side note. Never trust the result without checking also the flag. Okay? So the problem in the robust separation is find the strict separator such that we also maximize essentially the width of this separation gap. And using some clever math, which I'm not going to bother you with because it's quite involved, it can be actually shown that this width of this slab or this gap between those points is proportional to 2 over the 2 norm of A. So A is the tangent of the separation function that we are looking for. So essentially, what we would like to do is we would like to maximize 2 over the 2 norm of A, subject to those separation constraints that we had before. So A transpose xi plus B must be on one side, and for the y's, it must be on the other side of the separation function. Okay? Now the trouble of solving this optimization problem is that, well, try to classify. What kind of a problem is that? Again, we have linear constraints. We can easily convert them into non-strict inequalities by adding that positive tolerance and then normalizing by that tolerance. But what about the cost function? We know that we can easily solve two types of problems. Problems where the cost function is linear, that's the easiest problem. Somehow difficult or more difficult are problems which have quadratic cost function. And if we have a cost function which is neither linear nor quadratic, then we are in big trouble, because we cannot immediately solve those problems. So the question is the cost function quadratic? Quadratic meaning convex quadratic, because clearly also this is a quadratic function, but it is not a convex function. Okay? Actually, maximizing this function would be fine. We cannot minimize it easily. Okay? So is the function quadratic? So what is the 2 norm of A? How is that one defined? It's the square root of A transpose A. I mean, once we have square roots, no chance the function would be quadratic. The inner term here is quadratic, but then we have to take the square root, which completely ruins that. Moreover, we are maximizing this quadratic. So we are maximizing a function which is not even quadratic. How can we change this problem to minimize something? There are two ways. One, the one we are used to, which doesn't help at all. And then there is a better way. To maximize a quantity, say z, it's the same as minimizing 1 over z. Well, provided that z is always non-negative. Even better, positive, because we have to avoid dividing by 0. Okay? So minimization of the inverted value means maximization of the original value, right? So that's exactly what we are going to do here. Instead of maximizing this nasty term, we are going to minimize the inverted value. So we are going to minimize the 2 norm of A divided by 2. Now, this is still not a quadratic function, right? Because we still have that square root. But minimization of the square root and minimization of the square of the objective, so if we square this objective, then the two problems would have the same optimizer. So the A optimal that we would find from the green problem is the same as the A which would be optimal for the original problem. Now, why would we want to square the objective function? So let's just minimize 1/4 of A transpose A, because squaring removes this square root. Now, why did we do that? What did we obtain? What was the advantage here? The function is quadratic and convex. So if we have a convex quadratic function and linear constraints, how is the problem called which solves this kind of problem? What kind of optimization problem is a problem which has quadratic cost function and linear constraints? That's quadratic programming. So the general form of the quadratic programming is minimize 1/2 z transpose pz plus q transpose z subject to az less than b. Okay? So if we know that this looks like a quadratic program. How can we transform it to a quadratic programming problem such that we can then use the corresponding solver? In other words, what is P and what is Q? We don't care about A and B because they are the same as before. The constraints are the same as in the linear case.
P is 1 over half.
So P is just 1/2?
Because we have
The problem is,
so
remember, Z is A and B. Okay? So if I write this in some kind of expanded form, then we have Z transposed, which is A transposed B. Well, notice that B is just a scalar, that's why I'm not transposing that. Here, this P would be a 2 by 2 block matrix. Each of these elements would be a matrix itself, because A is a vector. Actually, this term here needs to be a scalar because it multiplies B squared times A and B. Okay? So if I call P1, P2, actually, we know that the matrix is also symmetric. That was the assumption for the quadratic programming that we had on the previous lecture. So that's why I'm putting P2. Actually, I should be more correct and should put P2 transposed here. Okay. So after expanding that, that's 1/2 of A transposed P1 plus times A, plus now we have 2 times B times P2 transposed A plus P4 times B squared. Okay? And here we might have also that Q, which is Q1, Q2, and here we have A and B. Okay? So that's Q1, now let's put transpose here, plus Q2 times B. Okay? So again, we are just comparing the stuff. Okay? So P1 here must be 1/2 clearly. Okay? Because we have 1/4 there. This one would be 0 because in this original cost function we don't have any product between B and A. So P2 would be 0. P4 would be 0. Q1 would be 0. Q2 would be 0. Okay? So that's how we can come up with the matrices of the cost function for a quadratic programming solver. And when we do this and solve the problem, and the problem is solvable, meaning it is feasible, then we obtain a strict separator because it would satisfy constraints. And not only that, it would also be a separator which has this large gap, or better to say, the largest gap between these points here. So we would in fact obtain the robust separator, which is the best one you can hope for. And actually the issue of robustness is quite important in practice, because essentially it means that if we would obtain some new point, then we have quite a large kind of chance that it would be classified in the correct manner. If this separator here would be really close to one of these points and then comes a point which is here, it would be classified to belong to the other side, which might be wrong. Okay? So usually in practice we aim for these kind of robust separators which can be solved as quadratic programming problems. So that was robust separation. And now we move to approximate separation. So the problem here is that if we would just solve either the linear or the robust separation problem with this particular set of points, the solver would just return a flag which says infeasible. There is no choice of the linear function which strictly separates the points. So clearly we would still like to find a linear separator, because we might throw in that additional logic that says,
So now there will be only a cost function and no constraint.
If there are no constraints, then the separator can also be like this.
No, when the objective function says that we are minimizing the number of points that are misclassified.
The question is how to characterize the number of misclassified points. For that, we still do need the constraints. But yes, that's the underlying idea. To essentially change the cost function to only minimize the number of misclassified points, but then we need constraints to represent those misclassified points. And this is how we do that. So notice that these were the original constraints after normalization of the strict separation problem. And these kind of constraints, they are called hard constraints, meaning either there exists some choice of A and B which satisfies all of these constraints, in which case the problem is feasible. If there doesn't exist any choice of A and B, the problem is infeasible. So these constraints are hard. They cannot be violated by the optimization algorithm. Actually, if we want to allow a case like this, we must allow some constraints to be violated. Okay? So the question now is, how do we say we are looking at this strict scenario here? How would we allow one constraint to be violated? For instance, this constraint to be violated. What do we need to do with the right-hand side? So say that this expression here evaluates to 0.1 in the optimization algorithm. Clearly, this violates constraints. How should we change the right-hand side such that this value does not violate the constraint? If you want 0.1 to be consistent with the constraint, what should be the right-hand side of the constraint? Well, it must be at least 0.1. Okay? It can be 0.2, it can be anything else. Okay? So the point here is that if we want to allow the constraint to be violated, because that's essentially what we are doing, we are allowing some constraints to be violated, but we would like to minimize the number of violations. Okay? So what we do is that we add some slack variable, let's call it vi here. And this slack variable, vi, must be non-negative. Okay? So if vi is 0, we just recover the original hard constraint. However, if the optimization algorithm sees that there is no choice of A and B which satisfies this hard constraint, then it will use this additional freedom, because now these vi's are our new or additional optimization variables. So we give the optimization algorithm more freedom to actually change the constraints if it is required to achieve separation. Okay? So here we have so-called softened. So we have converted the hard constraints to so-called soft constraints. So we have softened these hard constraints. How can we do something similar here?